Hello, this is Mr. Wakefield again, and we are now in our second to last section in Math 130, section 7.4. and the main topic is this thing called Binomial Theorem. We'll get to that in a few minutes here, but we need to kind of look at a few things first that'll help us with that. This thing right here with the funny looking symbols here, it's read like this. It's read as N choose R. I want to talk about that. There's a reason why they say the word choose right there. For example, let me, and you don't have to write this down here, but I'm just going to show you a simple real life example of this. Let's say, for example, that I had 4 people in a group right here. I'll just pretend like those 4 people are called A, B, C, and D. Person A, person B, person C, and person D. And let's say that I needed to pick 2 people out of that group for a particular project or something. How many different possible ways could that be done? How many different combinations would there be of 2 people chosen out of a group of 4? Well, that's what 4 choose 2 means, choosing 2 people out of a group of 4. You can see down here that if you write it out by hand, there are 6 different possible combinations. By the way, the order does not matter. So, like for example, if I chose BA, that would be the same thing as AB. Okay, when you're using this formula that I'm about to show you here, the order does not matter. So, and that's the case here when you're choosing 2 people out of a group of 4. Normally, you just pick 2 people. It doesn't matter who gets picked first. They're both in the group either way. So this would be a good. This is a good example. Choosing 2 people out of a group of 4. That's a good example of how this formula works. Then. So as you can see here, and I'll show you how this formula works in a moment. But ultimately the answer ended up being equal to 6. Which confirms this result down here where you can see there's 6 different combinations. So this formula tells you how many different combinations there are, and that's good news because I can't always write out all the different combinations. That's only something that's realistic if you have small numbers. If I said, for example, hey, how many, let's say I had 50 people in a group and I put a 50 right here, and then I said, how many different ways can I choose 10 people out of that group to form a new subgroup? All right, that would be much bigger numbers, and this would end up being a much bigger answer. But you definitely could not write that out by hand like I did here. Okay, you'd end up with a million different combinations approximately, and it would take forever to count up the exact amount. Anyway, this formula will work though whether it's small numbers or big numbers. Now, how does it work? Well, where I got this from is I got it from the top of your worksheet right here. Okay, where the 4 gets plugged into the n here because the top number is 4, so that would be the n. It gets plugged in here and here. And then the R gets plugged in here and here. But then what is the deal, though, with this factorial stuff, as they call it? The factorial is this thing right here that looks like an explanation point. All right, and that explanation point is what it looks like if you were writing something in English or Spanish maybe, or maybe there's other languages that use it as well. I'm not sure. But in math, though, the explanation point is a reference to something totally different. Okay, let's talk about that. 4 factorial, for example. Okay, that is 4 times 3 times 2 times 1. Okay, 2 factorial. That is 2 times 1. You might be able to be picking up on a pattern here. Let me just show you one more just in case. What is 7 factorial? 7 factorial, 7, 6, 5, 4, 3, 2, 1. All numbers being multiplied together there. Okay, there it is right there. And so the way factorial works is you start out with the number that's next to the explanation point, the factorial symbol. And you just count down by 1 each time all the way until you get down to 1, and then you multiply all those numbers together. And that's how it works. Okay, so 4 factorial, like I said, 4, 3, 2, 1. Okay, that's why it's equal to 24. If I multiply these four numbers together right here, it would be equal to 24. Down here, and by the way, factorials are similar to exponents when you do order of operations and you figure this thing out right here, okay? They are similar to exponents in that you do the parenthesis first, because parentheses come before exponents. Then you do the factorial. Then you do the multiplication here that's in between the factorials there. Just like you would with exponents. It goes after parentheses, but before multiplication. Okay, another thing that it makes it similar to exponents is that when you have a parenthesis next to a factorial, the factorial only applies to that parenthesis. So it doesn't apply to what's in front of that parenthesis there. And so that's why this is just, the second factorial is just for the second 2. It doesn't go over here to this 2 over here. So just want to make sure you're computing this correctly. So as you can see, it ends up being equal to 6 when I do order of operations. Figure out what the top and bottom are equal to, okay, and put it in lowest terms. All right, let's try that on a few more problems here. Okay, so what does this say right here? It says, how many different ways can you choose 3 people out of a group of 7? Okay, could I do that by hand? Yeah, it would be kind of tough. It would be a lot easier to use the formula here. Let's see how it comes out. 7 factorial. And then remember the r is the bottom number, so you plug it in here and here. Okay, and so that would give me 3 factorial. And then the parenthesis would be 7 minus 3 with the factorial next to that. And so what does that become? 7 factorial, if you put that in your calculator, 7 times 6 times 5 times 4 times 3 times 2 times 1, all of those things, that would end up being equal to 5,040. 5,040. And what about on the bottom, though? Okay. Again, you got to do parentheses first. Then you do the factorials before the multiplication. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is what? That is 24, as we just found out. Okay. So that ends up being what here? 6 times 24 is 144. So 5,040 divided by 144. Sorry about that. There it is. 5,040 divided by 144, when we get 6 times 24, we get that denominator. Now that I know what the numerator and denominator are equal to, what is this fraction equal to? Well, try to, since the numbers are big, okay, normally I wouldn't expect you to put that in lowest terms, but remember what I told you, when you got numbers that big, at least try to divide them straight through your calculator to see if it ends up being equal to a whole number. See if the 144 divides evenly into 5,040. Let's pull out our calculator and see if that works. Okay, so let's take a look at that here. 5,040 divided by 144. And you can see it does divide evenly. It's equal to 35. So that means that there's 35 different combinations of choosing 3 people out of a group of 7. Like that. Okay. Now, when it's written like this, it's the same thing as it mentions up here as it implies up here. It's just that the number that normally would go on top of this thing here that I like to call a skinny bracket right here, okay, that number that goes on top is the same as the number that goes in front of the C. Again, the C means choose, okay? So when you have a 5, like we do in the next problem, that goes first, followed by the C, followed by a 1, that is the same thing as this. First number goes on top, second number goes on the bottom. How does that come out? 5 factorial over 1 factorial. Again, you plug in the n and the r, okay, here and here. And then you subtract. You got to do it in the right order, though, okay? You got to go top minus bottom here. And then 5 factorial, that's 5, 4, 3, 2, 1. Multiplying all those numbers together, you get 120. 1 factorial, by the way, 1 1 factorial is just equal to 1 because you're not multiplying by anything else other than 1. Okay? 2 factorial is 2 times 1, so 1 factorial would just be you're just stuck on 1. You're not going anywhere. Okay? So 1 factorial is equal to 1. I'm sorry, I did that out of order there, though. It's going to come out the same, but I want to be consistent with staying in the same order of operations. Do your parentheses first. Now we can go ahead and do that. 1 factorial is equal to 1. 4 factorial is equal to 24. 1 times 24 is 24. And so now we know what the top and bottom are equal to on the fraction. And so now we have what? We have 120 divided by 24 is 5 if you divide that evenly. Okay. Next one here. Same thing as this, right? Okay. Now you might be wondering, how in the world do you choose 0 people out of a group of 4? You kind of don't, okay, but it's kind of similar to when we had an exponent of 0, okay? Exponents of 0 don't make much sense either. How do you multiply something 0 times? But what was this equal to, though? It was equal to 1. It's just something that we kind of accepted, all right? That's just the way it is. Well, as it turns out here, this is going to be equal to 1 as well. Not for the same reason, but it just works out that way. Let's see why. If I plug in the 4 into the n, and I plug in the 0 into the r, you'll end up seeing that this is equal to 1. Let's go ahead and compute that. So I figure out what the top and bottom are equal to here. You might be wondering, wait a second, what about 0 factorial? Again, similar to when you have a 0 exponent. Okay, 0 factorial is equal to 1. All right, again, how can you take factorial of 0 if it always starts out with a number that's bigger than 1 and it goes down to 1? All right, as all of these did. Again, it's not something that totally makes sense, but we make that equal to 1 because then it will agree with all of our other formulas that involve factorials. I won't get into why that always agrees. All right, that would take a while. We don't need to know all of that, but just trust me that 0 factorial being equal to 1 allows the formulas to work, the formulas that have factorials in them. Okay. Similar to a 0 exponent. 0 exponent being equal to 1 allows the exponent rules that we learned to work as well. You just got to remember that 0 factorial is equal to 1. So that gives me what? It gives me 24 over 24, which of course is equal to 1. And so whenever you choose 0 people out of a group of 4, there's only one way to do that. I guess you could think of it this way. Since there's only one way to do it, one way is to just say, hey, I'm not going to choose anybody. Okay? That's one way of looking at it. All right. The point is, though, is that no matter how you look at it, whenever this bottom number is 0, it's got to be equal to 1 each time. Okay. No matter how you interpret it. Next thing here is this thing called Pascal's triangle, and Pascal's triangle is this thing where it's going to help us figure out all of these skinny brackets here, where you choose a certain number out of a group. Okay. And that's really going to help us when we get ultimately to the big thing from this section, which is the binomial theorem. Okay, because these skinny brackets are going to have an indirect effect on the binomial theorem problems, and so the Pascal's triangle is really going to help us with this. Let me show you how to do the Pascal's triangle. The Pascal's triangle, it looks like a triangle or like a pyramid, okay, if you prefer. But they call it a Pascal's triangle. You always start out with a 1 on the top, and it's going to go in this it's going to have this shape here like this, like a triangle. Okay? And so what happens is, and the reason why it's going to look like that is because you're going to make a bunch of rows, and each row is going to have a certain amount of numbers in it. Each row will have one more number in it than the row above it. Let me say that one more time. each row will have an amount of numbers in it that's one more than the amount of numbers in the row above it. So the first row is always just the number 1. And again, that's just a single number there, right? So that means that the next row has to have 2 numbers. And then the next row is going to have 3, and then 4, and so on. They just want us to do the first 6 rows. You could go on forever with this thing, okay, all the way as far as you want, but they just want the first 6 rows. Okay, and that's all that we're going to need here, as you'll find out later. But because the second row needs to have one more number, that means it needs to have 2 numbers. But what you also need to remember is that, and this is going to be true for all the rows, the first and last number in each row is always a 1. So the 1s will be literally draped along the side of the triangle like this. It'll be all 1s on the sides, because the first and last number is always a 1. Now, since there's only 2 numbers in this row, okay, and since the first and last number's got to be 1, then those are the only 2 numbers in that row then. But the next row is going to have 3 numbers, and so that's different. Remember, the first and last number's got to be a 1. But that leaves an empty spot here in the middle. We got to have a third number, right? We got to have a total of 3 numbers. How you do that is you add the 2 numbers right above it like that. Okay. So then how many numbers does the next row got to have? It's got to have 4. Remember, the first and last number is always 1. Always start out with that. That leaves 2 blank spots here in the middle, doesn't it? How do we fill in those numbers? Okay, what you do is you add the first 2 numbers in the previous row, kind of similar to what I did up here with 1 plus 1 equal to 2, but you add the first 2 numbers, and then you add the second and third numbers, and that gives you the other one. So first and second, second and third, and that's how you figure out those 2 missing parts there. How many numbers does the next row got to have? 5. Because it's 1 more, again, it's 1 more than the previous row. All right, so that means that there's now 3 missing numbers in the middle, since we already have the 2 on each side here at the end, 1 and 1. So what are those 3 numbers in the middle going to be equal to? Again, similar to what we did in the last row, you go first and second, second and third, third and fourth. You add up those 3 pairs. So first and second is going to be 4. Second and third is going to be 6. Third and fourth number from the previous row is going to be 4. Okay. How many rows do we have now? We've got 1, 2, 3, 4, 5. And so we need 1 more row to complete the question here. Again, first and last number, always equal to 1. And what's the thing we've been doing on the last couple rows here? We always add up what? First and second, second and third, third and fourth, and you continue in that pattern until you get to the last 2 numbers in the previous row. And you add up all those pairs, and it will give you the 4 numbers that are supposed to be in the middle of this current row. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10. 4 plus 1 is 5. And that, you guys, is the Pascal's triangle. Again, theoretically, you could keep on going with this and just keep on doing more and more rows, but you don't have to here because the directions just ask for the first 6 rows. Okay? So, what is... how is that going to help us with this next part here? The next part here is called the binomial expansion. Okay, and the binomial expansion means to use the binomial theorem that's at the top of the page. Okay, use the binomial theorem. And what is that all about? Well, if you haven't seen the binomial theorem before, it can be pretty darn scary to look at it at first. I wouldn't blame you for thinking that. Let's take a look at it closely here. There's a lot of stuff going on here. You'll notice that the next 3 problems look like this, okay, where it's got 2 terms inside of a bracket and then an exponent on the outside. So we're going to take something that looks like this and we're going to make it look like this crazy thing right here. Again, it's not as bad as it looks, all right. I'm going to interpret this in the most easy way I possibly can, and I think that after you do it a couple times, you'll start to get used to it. There's a lot of patterns here, okay, that make it easier to remember when you start to see what those patterns are, and I'll show you that, okay. So let's jump right into it here. Notice that we have a bunch of those skinny brackets here, though. And the skinny brackets always start out with n0. Okay, well, what is n? N is the exponent there in the original problem that's on the outside. In fact, let's write down that right there. The n number is 4. The n, and again, I'm going off of the formula that's up here at the top. That number on the outside is called the n number. I know we have an n on the inside, but that's a different kind of n. All right, that's going to be your what? That's going to be your a and b terms right there. Okay, a and b. Okay, again, going off of this formula right here, we've got a and b, and then we've got the n. Okay, so the a is the m right here from the current problem. The b is the n, and then the 4 is the exponent on the outside. Okay, now, so let's see how this all works out. Since the n, meaning the exponent n, not the n on the inside, but the exponent n. Let me just clear. I know there's a couple of n's here, so I want to make sure we don't get confused here. The exponent n right there is 4, and so how it works is like this. We take 4, 0, leave some space, 4, 1, leave some space, 4, 2. The top number always stays the same, you guys. You can see I'm doing that here. The top number always stays the same in the binomial expansion. And it's always equal to the exponent on the outside. The bottom number always starts with 0. And it increases by 1 each time. And it keeps on doing it. You might be wondering, well, how long do I need to do this for? You keep on doing it until you get to the bracket where the two numbers are the same. See how the two numbers are the same now? 4, 4. That's when you stop. Okay. Before I tell you what those 5 skinny brackets are equal to, let's fill in the rest of the information. You'll see up here at the top that next to each skinny bracket, we've got almost all of them, we got the a's with some exponents here. Okay, the a to the n is saying what? It's saying to take the first term and take it to this power on the outside. Okay, and then in the next part there it says take that same term and take it to the power that's 1 less than that one. And then on the next one you take again the same first term and you take it to the power that's 2 less than the original one. The original one on the outside. Let me show you how that works. Okay, so the exponent on the outside is 4, right? The first term is m. So that means we're supposed to do m to the 4th, m to the 3rd, and you keep on decreasing the exponent by 1 each time. M squared, m to the 1st. And then the last one will have no m at all. No m at all, okay? So it goes M4, M3, M2, M1, no m at all. That's what you do with the first term inside the bracket. Okay. By the way, before I forget, put some pluses in front of each skinny bracket, except for the first one. You don't need it in front of the first one. Put all of those in there to separate that. Again, they go in front of each skinny bracket, except for the first one. Okay. But that's what you do with the first term there. Starts out with the same exponent that's on the outside, and then it just decreases by 1. 3, 2, 1, and then none. Okay, so don't put anything here at all for the first term. All right, on the last one, no m at all there on the last one. Then what you do with the b term, which is equal to n in this case, is you do exactly the same thing, you guys, except for you go backwards. Look up here, and you'll see what I'm talking about. It says in the last one here, you do b to the n. Just like over here, I did a to the n, first term taken to the n power. Now you're going to do the second term taken to the n power over here on the right. And then what happens is that the exponents decrease by 1 going this way. See how it goes B3, B2, B1, and then no B at all? So it's going backwards now. Let me show you how that looks in this problem. So in this case, the second term is n, and so we're going to say n to the fourth, n to the third, n to the second, n to the first, and then no n at all. So we did the same thing that we did with the first term with the m. We do that same thing here with the n. It's just that the exponents are going backwards now. Okay? They're decreasing going in this direction. All right. Let's keep going here now. By the way, why did I pick 4 to start with here? You always start with this exponent on the outside. Okay, whether it's the first term over here or the second term over here. You always start with that exponent on the outside and then you decrease it by 1. 4, 3, 2, 1 on the exponent there. Okay. All right, what you do next now is I now need to figure out what this is equal to. This answer definitely should not look like this. It should look like a normal polynomial with just a bunch of regular monomial terms being added together, added or subtracted together. We sometimes will see some subtraction in there as well, ultimately. Here's how you do it. It goes in 2 steps. The first step is you look at your skinny brackets, and here's the great news about this. You don't need to compute these skinny brackets doing the formula that we had up here. There's an easier way, okay, when you do the binomial expansion. In other cases, you need to do it this way usually. But in the binomial expansion, there's a shortcut, and it's using the Pascal's triangle. Okay, let me show you that. How many skinny brackets do we have? Count that out, and that'll be our big clue. We got 1, 2, 3, 4, 5 skinny brackets total, right? So all you have to do is go back up to the Pascal's triangle, and you count how many. I'm sorry, I said that wrong. You pick the row that has that many numbers in it. So since we have 5 skinny brackets, you just simply pick the row that has 5 numbers in it. Each row has a different amount of numbers in it, and so there's only going to be one row that has 5 numbers in it, and it's this one right here, 1, 4, 6, 4, 1. Okay, so if you had 6 skinny brackets, then you would have picked this row. All right, but since you have 5 skinny brackets, you're going to pick the row with 5 numbers in it, and that's exactly what those 5 skinny brackets are equal to. Let's bring those numbers down. 1, 4, 6, 4, and 1. Okay? And that's all you have to do to figure that out. It's a nice shortcut. You don't have to use that complicated formula at the top of the page for all 5 of these things. Very nice. What you do next, which is not overly necessary on this problem, is you also then take the first term and the second term to see how we raise them to powers here, m4, m3, m2. Normally at this point you actually have to figure out what m to the fourth is equal to, or n to the second is equal to, what all these things are equal to when they're raised to those powers that I wrote down. But whenever you take just a variable, just m, not m to the second, not 3m or 4m, but just m with, and it's just the variable only. When you take it to a power, there's nothing to compute. M to the fourth is just m to the fourth. So just bring that down. On the next couple problems, we'll have to do some more work on that, on the exponent part there. But m to the fourth is just equal to m to the fourth. Okay. If it had been 2m inside of a bracket taken to the fourth power, then we've got some work to do. And we'll see that kind of thing coming up. Okay. Bring down your pluses in front of the skinny brackets there, and they're still in the same place. And then we have right there. You don't have to put those multiplication symbols in there. As long as you know that all 3 of these parts are being multiplied together here. These 2 parts are being multiplied together here. I put the multiplication symbols in there to emphasize that, but you don't have to do that normally. But just to emphasize that. Okay. What is m to the first? it is just m. And then bringing down the rest here. Again, I'm bringing down these things and not doing anything else with it because, again, there's nothing you can do when you have a variable taken to a power, and that's it. This is also multiplication right here as well. Okay, the skinny bracket with the thing next to the term next to it, that's multiplication. All right, just like it normally would be. So we're pretty much done. This is actually you could leave your answer like this because this is a normal polynomial. It's just that I put all those dots in there to indicate the multiplication. Again, I put that in there because that's what we're normally going to have to do in some of the bigger problems coming up here. But it's going to end up being the same thing as this, other than the fact you can get rid of you don't have to write those ones there. But yeah, normally what you would do, and it's not going to change the problem much. That's why I said you don't really have to do this, but you could get rid of those ones though. But what we would normally do, and this is good practice for the next couple of problems, is after you do that previous step there, where you do the exponents and you figure out what the skinny brackets are equal to, one more step to go, you figure out what these 5 groups are equal to by multiplying the different pieces together. And the reason why I know it's 5 groups is because the groups are separated by these pluses that are in front of each of those skinny brackets. So we figure out what those 5 groups are equal to. 1 times m to the 4th is m to the 4th. Bring down the plus right there. 4 times m to the 3rd times n. Again, that's just 4m to the 3rd n. Like I said, in this problem, and most problems aren't like this, but in this problem, it's just nothing's gonna really simplify there. It's just gonna stay the same when you multiply those things together. Anytime you multiply a constant times a variable times another variable that's different than the first variable, it just kind of smushes together. There's nothing that combines. Okay, bring down the plus again. And that same thing happens on all the rest of these. All right, but again, normally there will be things that combine, but just not on this one. Like we usually do, we start out with a simpler problem, and then we build up to the bigger ones. This is no exception. 1 times n to the 4th is n to the 4th. You could keep the 1 in front of that whenever your coefficient is 1, but as usual, you don't have to. So what we have here is we have... let's review here. You've got the skinny brackets. Okay, you write those out. You do the first term with the decreasing exponent, okay, until you get no first term at all here. The m is gone here on the last term. And then with the second term, you do the same thing but the opposite way. You start out here and you work your way to the left. N4, N3, N2, N1, and then no n at all. And then you do those last 2 steps as we talked about. So hopefully this is starting to kind of stick with you here, all right, in your mind. But we'll do a couple more examples here just to make sure that we're starting to get this. We'll see some new details in these examples coming up on the back side as well. But the main thing, though, is just getting used to these different aspects of the formula that we're supposed to use with the skinny brackets and the exponents going from big to small and all that stuff. So we'll be getting used to that more here as we go along through the next couple of problems. Okay. Okay, now let's go ahead and flip it over to the back side and take a look at those 2 problems that we're talking about. In number 6, looks kind of like a lot like the last problem. The difference is that instead of having the n, you have the n squared. It's going to make the problem look a little bit different, but the process is still basically the same. This time the exponent is 5 on the outside. And so what that means is when the exponent is 5, instead of having 4 choose 0 as the first skinny bracket, and then 4 choose 1, and then 4 choose 2, and so on like we did in the last problem when the exponent was 4 on the outside. Because it's now 5, we're going to go like this. We're going to have 5 choose 0, 5 choose 1, and then you just keep on going 5 choose 2, and you keep on doing this until you get to 5 choose 5. Again, leave some space in between each one to fill in the rest of the information, just like we did in the last problem. Okay, and you end up when you stop when the two numbers are the same. Just like in the last problem when we had 4, 4. Okay, so that's the skinny brackets. Then we do the thing where you take the first term and you take it to the power on the outside. That's the first part. And then you take the same term, that same first term m, and you do the same thing over here, but you decrease the exponent by 1. So m5, m4, m3, m2, m1, and then no m at all in the last one. Again, put pluses behind or in front of each bracket, each skinny bracket, except for the first one. Don't forget to do that too. Now, what's different about this problem is that now you're supposed to take the second term, and we did that in the first problem that we did, but you take the second term, and because it's more than just a variable, you need to bracket it like this, okay, before you take it to the power. Remember in the last problem we had n to the fourth, n to the third, n to the second, n to the first. Well, now we have n squared, and so we need to bracket that to make sure we're taking that whole thing to the appropriate power. What power is that? It is going to be, again, you always start out with the power that's on the outside, 5, and then you decrease it by 1 each time. Not the inside exponent, okay? That's the term you're taking to that power, but the power that you take it to, it decreases by 1 each time. So you got n squared to the fifth, n squared to the fourth. Okay, so you start out with the exponent that's on the outside like usual. You decrease that by 1 while keeping the term on the inside the same. But the power you take that inside term to decreases by 1 each time. So n squared to the fifth, n squared to the fourth, n squared to the third, n squared to the second, n squared to the first, and then no n squared at all. All right, so same process as in the last problem, but you just need to bracket the entire term there. All right, the only time that we wouldn't bracket it is if it's just a variable like m with no exponent and no number in front of it and no negative sign either in front of it. It's just a variable m. Or if it was just a positive constant number. Okay, that would be the only other time. We're not going to see that here in these problems here, but I just want to let you know. Otherwise, you do want to bracket your terms before you take them to their appropriate powers. Okay, 5, 4, 3, for example. What did we do in the last problem, you guys, after we set up this first step here? Two things on the next step. We first of all figured out what these skinny brackets were equal to. It's going to be something different this time because there's 6 skinny brackets this time instead of 5 like there was in the previous problem. Okay, the way we figured it out was since we have 6 skinny brackets in our problem, we picked the row that has 6 numbers in it. There will be only one row with that many numbers, and it's this last row right here. So you just simply take those 6 numbers, and those 6 numbers will then be equal to the 6 skinny brackets that we have here. 1, 5, 10, 10, 5, and 1. Okay. Then you take, like I said in the last problem, you take the first term and the last term, and whatever exponent they're taken to, you actually figure that out. If you have just a variable, though, like m taken to the power, that's not going to do anything. You try to figure out what that's equal to, but m to the fifth is just going to stay as m to the fifth, all right? That's just what it's equal to. On the other hand, though, bring down the plus there. On the other hand, n squared, when you take it to a power, now that's something you can compute, okay? So m to the fourth stays the same since it's just m to a power. N squared to the first, 2 times 1 is just 2, all right? And we knew that anything to the first power is going to be equal to the same thing anyway, but that's how you would do it, though, normally, is you multiply the exponents, okay? In fact, as we move on to the next problem here, remember we said way back in the prerequisite review packet, and we've done this, and this is the prerequisite review packet, but we've done this in other situations this semester as well. But when you have a single term, you guys, inside of a bracket, and you have an exponent on the outside. Just a single term. I'm not talking about when you got two terms here. That's a whole different thing. Okay? Otherwise, we wouldn't have to do all this work here. It would be a much simpler problem if it worked with two terms on the inside as opposed to just one like we have here. But if you have one term on the inside taken to a power, remember you multiply the exponents that are attached to the variable. Okay? And if the coefficient is 1, you can skip that part like it is here. It's just 1n squared. You multiply the exponents. So that 4 times 2 is 8. 6 times 2 is 12. All right, so in a likewise fashion, n squared squared, 2 times 2 is 4. Okay, and then we bring down the m to the third as well. Notice, you guys, that I've been bringing down these things. Like I said in the last problem, we multiply the different parts together. These two parts here, these three parts, these three parts. All the middle terms here, the middle groups, are going to have 3 parts to it. This one, this one, this one, and this one. The outside parts will just have 2 parts, the skinny bracket and then the single term there. However many parts there are, whether it's 2 or 3 like in the middle groups, you're going to say that they're being multiplied together, and then we'll actually do the multiplication on the next step. Okay, if it's necessary to do. Bring down the plus. 10 times the m squared is just m squared. But then this is what? 2 times 3 is 6, and so that's going to be n6 coming down. M to the first is just m right there coming down. N squared to the fourth, 2 times 4 is n to the 8th. And then finally this last one here, 2 times 5 is 10, so that's going to be n to the 10. Okay, and that is that step right there where you do the skinny brackets and the exponents. The last step you do, as I mentioned in the previous problem, is you take these groups that are separated by the pluses. There's 6 of them this time, isn't there? 6 total. That are separated by the pluses that are in between them, okay? And we actually multiply the different pieces together inside of each group. Like I said, the first and last group will have just 2 pieces. The 4 middle groups here will have 3, and you can see that. 3 parts here that are being multiplied together in each group. All right, so 1 times m to the 5th is m to the 5th. Bring down the plus. 5 times m, 4 times n squared. Again, like I said in the last problem, and this won't happen in the next problem, by the way. That next problem will be a little bit different. But when you have just a constant times a variable, where the variables don't have any constants in front of them specifically, but just the constant over here, when you have 5 times a variable, it just smushes together, okay? When you just have 5 as the only constant. There's nothing more to combine there, like I mentioned in the last problem. Same thing here. But the next problem will be different, like I said, so watch out for that. 10 times m3 times n4 is just equal to those 3 things smushed together like that. Bring down the plus again, and then these last, or these next couple ones are also like that. So let me just bring that down. And then finally, this last part here is 1 times n to the 10th. And we know that 1 times anything is itself. And so that's the last step, is to multiply the different pieces of each group together. And it gives you a normal looking polynomial at that point. Okay? Moving on into the last problem here. Again, you can see that the exponent on the outside is 5, so it's going to have the same amount of skinny brackets as we had in the previous problem, since that also had a 5 on the outside. Again, the exponent on the outside tells you what to put on the top of each skinny bracket, and then the bottom is always starting with 0, and then it goes up by 1. So 1, 2, 3, and then you keep on going until the 2 numbers are the same. Just looking at the skinny brackets right now. So that means that we're going to have the same thing as the last problem here. 5, choose 0. 5, choose 1. 5, choose 2. I'm going to make a little bit more room than last time here because this problem's a little bit bigger. There we go, like that. And then we then do that same thing we did in the last problem, which is to take the first term. Since it's not just a, since it's not just a variable with no exponent and nothing in front of it, but it's actually 4a, because of that, you need to bracket it on each step here. Bracket it on each step, and then what do? You start out with the exponent on the outside, 4a to the 5th, and then 4a to the 4th. Okay, so keep the entire term intact here. 4a, 4a, 4a again. Keep on bringing that down. Okay, but you just change the exponent by decreasing it each time. 5, 4, 3. So the next one's going to be 4a to the 2nd, 4a to the 1st, and then no 4a at all in the last part. And then for this part here, we need to talk about that for a moment here. If your second term, you guys, has got a minus in front of it, then that means that you do not do 5b. You do negative 5b, okay? You need to include the negative if it's minus, okay, when you actually do this step here. So we're going to do negative 5b to the 5th. Again, we start out with the same exponent that's on the outside. It's just that we start out on the right instead of on the left when you do the second term here. So negative 5b to the 5th. Make sure to bracket that because it's not just b only. Okay. Negative 5b to the 4th. Negative 5b to the 3rd. Okay, leave enough space to put a plus sign in front of each skinny bracket here, by the way. Okay. Negative 5b to the 2nd. Negative 5b to the 1st. And then no negative 5b at all here. Okay. What do we do on the next step after we do that entire setup right there with the skinny brackets, the first term and its exponents, the second term and its exponents going the other way? After all that's done and we're done with that first step, we then do what two things on the next step? We figure out what the skinny brackets are equal to, and then we figure out what the exponents are equal to when they're applying to the things that the first term, the 4a, and the second term, negative 5b. I'll figure that out in a moment. But what are the skinny brackets equal to again? Well, because there's 6 skinny brackets, all right, just like in the previous problem here, number 6, because there's 6 skinny brackets here, you pick the row that has 6 numbers in it. Okay, it all depends on how many skinny brackets you have. So let's say, for example, you had a smaller problem where it had only 4 skinny brackets. Then you would pick this row that has 4 numbers in it, and that would be what the 4 skinny brackets are equal to. But because the current problem, once again, has 6 skinny brackets, we're going to pick this row right here. Okay, let's do that. We got 1, 5, 10, 10, 5, and 1. Now the number's going to get kind of big here. Okay, be patient here. Use your calculator, okay, if need be. 4a to the 5th. Remember, as I mentioned over here, actually I didn't completely review it yet, but when you have a coefficient that goes with your single term here, all right, here's what we're looking at right now. Okay, if you've got a coefficient, not just x, with your single term that's inside the bracket here, then just like we do with the negative 3 here, we need to do the same thing with 4. You need to take 4 to the 5th power. You don't need to bracket it when it's positive, but you do need to do 4 to the 5th. If you put that in your calculator right now, that would be 1,024. 1,024. So this thing right here then would be equal to 1,024 x to the 5th. X to the 5th because it's 1 times 5. X to the 1st, 1 times 5 gives you x to the 5th. So we get 1,024 x to the 5th. Bring down the plus. Let's do that same thing again here. 4a to the fourth. What is 4 to the fourth? That is 256. You can put that in your calculator. It'll tell you that. And so 4 to the fourth is 256. The a to the fourth is a to the fourth. 1 times 4 is 4. But you also got to do negative 5b to the first. But we know that anything to the first power is equal to itself. Okay? And so and by the way, keep that in brackets because it'll look like subtraction if you don't. Okay, if you're multiplying by a negative, you want to keep the negative in brackets there to avoid it looking like subtraction, which is not. It's supposed to, all three of these parts are supposed to be multiplied together here. The answer you get from the skinny bracket, and then the answer you get from each of the two terms being taken to a power. Those three parts need to be multiplied. It now looks like multiplication right here because I put the bracket there. Bring down the plus. Okay. 4a to the third. 4 to the third is 64. A to the third is a to the third. What about negative 5b squared? Well, again, we have a single term inside of the bracket taken to a power, and so you need to take the coefficient to that power, put it in brackets if it's negative to make sure to do it correctly there. If it's negative, you have to do that. And that would be 25 there, wouldn't it? That would be 25. And so we get 25, and then b to the second power is just b squared. 1 times 2 is 2. Okay. Bring down the plus. Okay. Next one here, 4a squared. 4 squared is 16. Again, you remember you're multiplying all the different parts together here, so I brought down the multiplication symbol. Times 16 what? A squared. And then negative 5b to the third. What is negative 5 to the third? Negative 5 to the third is negative 125. Okay. If you don't want to put a negative sign in your calculator, you don't have to. Remember, when you're taking a negative, just a normal negative number, negative constant number to a power in your calculator, you can just take 5 to the third and then realize that anytime you have a negative number to an odd power, the answer is going to be negative automatically. If you have a negative number to an even power like we do over here, it's going to be positive automatically. So you can just say 5 to the third in your calculator and then figure out the sign of the answer by realizing that negative to an odd power is negative, so make that negative. Negative to an even power is positive, so make that positive. Okay, so just a little way to make it a little bit easier to use your calculator there, that's all. So here, this is going to be negative 125b to the third. Okay. Bring down the plus there. Okay. And 4a to the first is just 4a. Negative 5b to the fourth. Again, what is negative 5? We already know what the b part is. But negative 5 to the fourth. Same thing as 5 to the fourth, because the answer is going to be positive when you take a negative to the fourth power. That's going to be 625, and then b to the first taken to the fourth power is b to the fourth, like that. Bring down the plus, and then negative 5b to the fifth. What is negative 5 to the fifth? Negative 5 to the fifth. You could do 5 to the fifth on your calculator, which is 3125. But because a negative number to the odd power is negative, it's actually going to be negative 3125. And so this is going to end up being 1 times negative 3125, and then take the b to the fifth right there, like that. Okay, so some big numbers here, right? Okay, but that's why we got calculators. Once again, just like in the previous couple of problems, okay, you take your groups that are separated by the pluses there, and you multiply the different pieces together. Again, the first and last group will always have two terms, or two things to multiply together. And then the middle groups, 4 of them here in the middle, they will have 3 parts to multiply together. Again, calculators will really be handy here. 1 times anything is itself, so that first part there is 1024x to the fifth. Now, normally I would bring down the plus here, but as you'll see here, it's going to change to minus because this next part here is going to be negative. I'll show you why. 5 times 256. So 5 times 256 is going to be what? That's going to be 1280, and then we still got to multiply by the other 5 there, and I'll get the negative in there as well. And that's going to be 6,400. So this is going to end up being 5 times 256 a to the fourth is going to be 1280 a to the fourth. But then when you multiply by the negative 5, that's going to be negative 6,400. Negative 6,400. All right. A to the fourth b. Okay. Because you got to multiply by the a to the fourth and the b there as well, of course. Bring down the plus. This time it's going to be positive, and so you do bring down the plus. Why did I make this minus now? It's because I ended up with a negative group right here. This group right here is negative, and so adding a negative, as you know, when you're setting up a polynomial, which is what this answer ends up becoming each time when you do the binomial expansion, if you have a polynomial and you are adding a negative, you can just change that to minus. We've seen that a number of times when we've dealt with polynomials in the past. Okay, plus a negative, plus negative 6,400 is just the same thing as saying minus 6,400. Okay, you could say plus negative 6,400 a to the fourth b if you wanted to, but this is the more traditional way of doing it. All right, anyway, next one. 10 times 64 a to the third is going to be 640 a to the third times 25b squared. So we're going to need to do 640 times 25 there, aren't we? So that's going to be 16,000 on the coefficient part. And then a to the third times b squared is just a to the third b squared. Okay. Can't combine those variables because they're not the same. Next part here, we got 10 times 16a squared is 160a squared, but then we need to do the 160a squared times this. So we got to do what? We got to do 160 times 125, exactly 20,000. But because of that, we did 160 times negative 125. It's actually going to be negative 20,000. Negative 20,000 what? A squared b to the third. Okay. Next part here. 5 times 4a. That's 20a. 20a times 625b to the fourth. We have to do what? We have to do 20 times 625. So that's 1250. And it's going to be positive this time because I only multiplied positive numbers there. There's no negatives. And then we have times a times b to the fourth. Last one here, you're just multiplying 1 times this big term right here. And so, of course, that's going to be equal to that big term. Because it's negative, I'm going to say minus. Again, you could say plus negative, but that's the same thing as saying just the minus right there. So a really big polynomial. You've probably never seen one that big before with that big of numbers. All right, I don't normally see anything like that either. That's what it is. So we did the same steps we did in the previous problems. It's just that the numbers were a lot bigger, and therefore it took us a little bit longer to do it. As you can imagine, if you tried to multiply this thing out by hand, some of you might be thinking, okay, instead of doing the binomial expansion with all this stuff, could I just multiply this bracket 5 times? Because when you have a bracket attached to an exponent of 5, that means to multiply the bracket 5 times. They don't want you to do that here because they asked you to do the binomial expansion. Okay, so don't do that there if they ask you to do the binomial expansion. But I think you can imagine that, at least in this case anyway, it would have been a nightmare to try to do that because of how big the numbers get. Can you imagine having to multiply those brackets out and ended up with all these big numbers, and you would have had a whole bunch of terms, okay? Because when you, as you know, when you multiply out brackets with two terms in it, you oftentimes end up with a bunch of terms, especially if you have more and more brackets you got to multiply. And then imagine having to combine like terms with numbers this big, okay, which is what usually happens at the end of a problem like that when you're multiplying brackets together with multiple terms in it. And so as hard as this was to do all this stuff, and it will get easier the more you practice it, but as hard as this was, compared to the alternative, I think it wasn't a bad thing for us here. But please do, when they ask you to do that binomial expansion, you have to do that even when the problems are a little bit easier, like up here where the numbers aren't as big. Okay, because we want to make sure that you know how to do that binomial expansion for situations where it's more advantageous to use that. Okay, so we need to make sure that you've learned that. Okay, so make sure to follow the directions, and if they ask for the binomial expansion, you have to do what we've been doing here in the last three problems. Okay. And I just realized, by the way, you guys, that I made a little misprint here. This should be a to the fifth instead of x to the fifth. You may have noticed that already. Sorry about that. Okay, it took me a while to realize that. So let's fix that. Again, the variable there is a, not x. All right, so anyway, that is it for number 7 and also for section 7.4. As usual, let me know if you have any questions about this. You have a good day, and we'll see you back for the very last section of Math 130, and that would be section 7.5 in the next video.